Hello, and welcome to lesson number 2 in our area and volume of scale diagrams lesson. Today we're going to take a look at scale volume of models and how the volume of a model compares to the actual using our scale factor, which our scale factor is useful when we're dealing with the dimensional change, with the area change, and then with the volume change. With all those things, we can use our scale factor. So let's do a little bit of an experiment, okay, a little bit of a test here to see if we can figure out what we're going to do to come up with volume. And maybe you've watched video 1 already and you already know, but not, that's okay. Let's take a look. So here's going to be our nice little cube. We have a 2 by 2 by 2 cube, okay, nice and simple little cube. Let's increase it. Oh, sorry, it's got a volume of 8, okay, 2 times 2 times 2, volume of 8. Let's increase the size by a scale factor of 2. That means that every dimension is going to be increased by a factor of 2, which means that we now have a cube that is 4 by 4 by 4. What is the volume? Well, it's 64. Okay. If we divide 64 divided by 8, we get that this is 8 times bigger. So a scale factor of 2 on the dimensions makes a scale factor of 8 on the volume. Is there a correlation? Well, quickly thinking, yeah, maybe there is. Okay, okay, so there we go. So when the length is doubled, the volume increases by 8 times. Let's try another one. Let's use a k value or a scale factor of 3. So now instead of a 4 by 4 by 4 cube, we have a 6 by 6 by 6 cube. It's 3 times bigger than the 2. This has a volume of 216. Do the same division here. Okay, 216 divided by 8 is equal to 27. Okay, so when the length is tripled, scale factor of 3, the volume is increased by 27. That's a much bigger number. It's getting bigger very quick. Okay, how are they related? Okay, when dealing with volume, the scale factor is cubed to determine the factor of the volume is changing by. So this means that what we're going to do here is our formula is going to look like this. Scale volume is equal to the actual volume times the scale factor cubed. So I'm going to use a little example here. When they are making a statue in front of the school of me because I'm such a great teacher, yeah, right, okay. If they make it twice the size, dimensions, the volume will be 8 times the volume of me. Okay, so you can think of it that way, right? They got to cube the scale factor in order to come up with that. All right, so scale volume is equal to actual volume times k cubed. So now we've got to cube our k value. All right, so now what does this look like? I'm going to bring back the area in there as well because we've talked about that in a previous lesson. So when we have a length of, or when our k value is 1, k squared is 1, volume is 1. So in other words, when we have the original shape, it's got the original area and the original volume. Okay, so that's what that means. When we double the size of the lengths, we have 4 times the area and 8 times the volume. Okay, k squared, k cubed. When we triple the length, we have 9 times the area and 27 times the volume. And finally, when we quadruple the length, we have 16 times the area and 64 times the volume. So if you increase all the dimensions by 4, you are getting a way bigger volume on that object, whatever you're happening to do that with. Now let's go the other way. Okay, so back to here. If we have half the length, a quarter of the area, and an eighth of the volume. So if we start making it smaller, our volume gets really, really small very, very quickly. A third of the length, 1/9 the area, and 1/27 the volume. And a quarter of the length, 1/16 the area, and 1/64 of the volume. So I'll give a little example of this. You have a model car. It is 1/4 the size of the original car, which doesn't seem like much. But the volume, or maybe even the weight of it, is 1/64 the size. So it's way smaller weight-wise, which is why you can carry around a car that is only a quarter the size. Maybe, maybe not. Okay, but that's why. Okay, because it's the volume has been shrunk by so much, even though the length is not as much. Now, if you go back to, or if you think of a car that's even smaller, so let's say 1/64 the size of the length, right? The volume is absolutely microscopic compared to the original, which is why a little toy car is very easy to carry around, whereas the actual car is a little bit more difficult to carry around. Just a little bit. All right, let's do some examples here. We have a basketball. It is 4 times as wide as a baseball. If a baseball has a volume of 12.25 cubic inches, what is the volume of the basketball? All right, now pause the video here. See if you can come up with the answer using that scale volume formula. I'll put it up on the screen there as well. And if you can, awesome. If you can't, that's okay. Unpause the video once you're done, and we'll go through the answer together. All right, a basketball is 4 times as wide as a baseball. That means that from a baseball to a basketball, okay, we have a scale factor of 4. Okay, now baseball is original, basketball is our scale. Okay, so actuals are baseball, basketball is our scale. That means that our actual volume is 12.25 cubic inches. It also means that when we put this into our formula, okay, actual volume times scale factor cubed, remember, don't cube the 12.25, okay, that's a measurement. Cube the 4, okay, that's what when we're going to cube, we should get a scale volume of 784 cubic inches, okay, which is why even though a basketball is not much wider than a baseball, it is way bigger, way more volume, okay, because it's, again, a sphere. All right, so the basketball has a volume of 784 cubic inches. All right, perfect. All right, here we go. Next one. Campbell's has made a giant soup can that is a scale model of their original tomato soup can. The model has a volume of 350 liters, and if Campbell's uses a scale factor of 10, what is the size of their original can in milliliters? All right. So there's our formula if you need. Pause the video, come back when you have your answer. All right. We are trying to find the actual volume. We're given the scale one, the really, really big one. We're given the scale factor of 10. We now need to find what is the actual volume. So we've got to rearrange our formula a little bit. We're going to divide by k cubed. And so our actual volume is equal to scale volume divided by k cubed. Plug those numbers in, 350 liters divided by 10 cubed. And we're going to get 0.35 liters. Well, there's 1,000 milliliters in a liter, so therefore the actual volume is 350 milliliters, which if you look really, really closely at that little can, it says 350 milliliters on the side. Look at that, using actual stuff. That doesn't always happen, but in this case it did. All right, so the original can has a volume of 350 milliliters. Oh, there we go. All right, here's the next one. Seaflow makes a number of different gas cans. The 10-liter and 20-liter cans are similar. How much larger is the big can than the small can? So we're looking for K. Okay, so I'll throw the formula up there again. Try to solve it. If you get an answer, awesome. If you don't, that's okay. Unpause the video when you have your answer. All right, so we're looking for our K value, and we are given 2 volumes. Liter is in volumes. So we're going to rearrange our formula to look like this. K cubed is equal to SV over AV, or K is equal to the cube root of SV over AV. I would really recommend that you practice doing cube roots on your calculator to make sure that you get the right answer. So follow along with this one, give it a shot, because we haven't done cube roots a lot, maybe a little bit here and there, but it's good for practice. So plug the numbers in. 20 divided by 10 is 2. The cube root of 2 is 1.26, which means that the large can is 1.26 times bigger, okay, dimension-wise, than the smaller can. Now, here's the next part. If the small can is 40 centimeters tall, how tall is the larger can? Well, I'll go through this one with you pretty quick here. We're going to use our dimension formula. Our K value is 1.26. Our actual dimension, the small one, is 40 centimeters, and therefore the scale one is only 50.4 centimeters tall, which isn't that much taller, but we've increased all the dimensions and doubled the size of the can. All right, so the original can, 50.4 centimeters tall. That is the end of this lesson. Please make sure that you are aware of squaring and cubing our K value, okay, whether you're dealing with an area or a volume. Be careful with your formulas. Make sure you know which one is the actual and which is the scale. Just pick one that you think will work best for that. Thank you so much for watching. Have a wonderful rest of the day.